The Rayleigh genes catastrophe. This first video will delve into the mathematical concepts behind the creation of a classical model for blackbody radiation. A key item that I want to cover in this video is to demonstrate the work of theoretical physicists in problem solving, which to me is very interesting, and which offers a different approach than just a lecture on the topic. Note that I will attempt to give you a conceptual understanding of where each expression comes from without the need to bog down the video with slight mathematical nuances. To begin, what is a blackbody? Most objects absorb and reflect incident light, but a blackbody absorbs all of it. It is a perfect absorber of electromagnetic radiation. Another important quality of a blackbody is its emission of light based on its temperature. As the temperature goes up, it emits more light. Blackbody emits radiation to reach thermal equilibrium, making it also a perfect emitter of radiation. An example which demonstrates how a blackbody works is a metal rod. As the temperature goes up, it starts to glow, which is the emission of radiation. A question remained as to the qualities of the electromagnetic radiation emitted based on its temperature. As a blackbody emits all the wavelengths of the electromagnetic spectrum, experimentalists wanted to study how qualities change for each wavelength. Specifically, they wanted to measure how spectral radiance emitted by a blackbody changed with the wavelength of electromagnetic waves emitted. The idea of spectral radiance is not known by most, but it is simply just the intensity emitted per wavelength, or in other words, the energy per second per area per wavelength, which is a bit of a mouthful. Using an experimental device to mimic a blackbody called a Jean cube, Otto Lumbar and Ferdinand Karlbaum ran a brilliant experiment and found these beautiful graphical representations of spectral radiance. The question on the mind of some theoretical physicists of the late 19th century, particularly John and Rayleigh, was how to represent this radiation deriving completely from their known theories of physics, being thermodynamics and electricity and magnetism, or electromagnetism. And so they began. To solve this problem, they used a setup of a cube representing the Jean cube and wanted to find the energy density in the cube. This is because it is proportional to the spectral radiance and is easier to find. Since inside of this cube we are dealing with light, we'll use electromagnetism to count the number of waves, and then use thermodynamics to find the average energy of each wave. Combining those two results, we can get the energy density. We will employ the concept of a wave mode, which is simply an arrangement that a wave can take. It will depend on the frequency of the waves inside. The way to mathematically solve this is to find the energy that each wave mode has, and then count the modes in between frequency and the differential frequency. Counting the nodes between this nu plus d nu and nu gives us what is called the density of states, which is the modes per frequency per volume. And this is a very useful quantity because if we multiply this by the energy of each wave per frequency, we will actually get the density of energy inside the blackbody, which we can easily get the spectral radiance from. Inside the cube, there exists a boundary condition that there cannot be the existence of any electric field at the walls. This is because it's a perfect conductor. And what this means is that the wave function's value must equal 0 at each side of the box. Similar to a rope with both ends stationary, this forces all the waves inside of the cubes to become standing waves. We can start with a simple wave in one dimension given by this equation. Combining the wave equations for simple right and left moving waves, we get a new equation for the standing waves in each direction. If we take into account one dimension of this wave, mathematically, what we know is that this equation must satisfy the boundary conditions of being equal to 0 at x equals 0 and x equals L, the length of the box. From the standing wave equation, we can plug in the boundary conditions and get this result. What is interesting about this result is that only certain wavelengths of light are permitted, given by this relationship relating wavelength to a positive constant m and this constant denotes the possible state of the standing wave, which is a bit cryptic, but I'll go into it later a bit. This 1/2 comes from the definition of the standing wave, in which the integer number of half-wave cycles fit into an interval. That's the definition. It is important to note that even though there are a discrete amount of states, meaning like 1, 2, 3, 4, the waves themselves and everything about them is continuous. It's still perfectly classical, no quantum stuff yet. A question that I asked when researching this topic is, what does m, the constant, physically represent? In a standing wave, a mode, as we call it, is an allowed standing wave pattern. This constant m is called the mode number, or in other words, the number of half-wave patterns for each dimension. So, looking in the x direction, let's say we have mx mode x equals 3. That would mean that there are 3 half-wave patterns in the box, and if you go up, then down, then up, there are 2 places where the value is 0, and we call these places nodes, so there are 2 nodes. Finding an equation for the mode number with respect to the frequency and the length of the box and some other constants, we can get this equation, which now we can generalize into 3 dimensions. Notice that this equation is squared because it makes the math easier. The next step is to actually solve for the density of states, which is the number of combinations of mx, my, and mz that can fit inside nu and nu plus d nu, the frequency differential. It turns out that the easiest way to do this is to imagine a sphere of radius r, and then find the volume of states from r to dr. We can set the radius equal to the Pythagorean sum of the mode numbers, and then get an expression for the radius with respect to the frequency and length. In differential form, we can now find the volume and get an expression for the density of states, d mu. Now that we have found the density of states, we need to find the average energy of these waves, the second part of the problem, which we can use Boltzmann's work on the equipartition of energy to find. I will not go deep into why it is like this, but per the equipartition theorem, the energy of each wave in this scenario is equal to Boltzmann's constant times the temperature. If you want me to make a short video going into why this is, please let me know down in the comments below. Combining these two expressions, we get that the energy density per unit frequency is equal to this expression. If you have taken an algebra class in high school, you should probably see that this expression is clearly wrong, as it is very different than the expression got earlier by the experimentalists. To solve this problem, we would need to wait a couple years for Max Planck to come in with his mathematical idea of energy quantization. This failure of classical mechanics was dubbed the ultraviolet catastrophe. I made this video to go over the history and techniques used to solve this problem by theorists of the time. Please let me know if you want me to make another video going over to the solution by Max Planck of this problem, and how is the catalyst for the new quantum revolution, and if you have any other comments or suggestions. As always, thank you for watching my video, and don't forget to like and subscribe, as I spent a lot more time than I would like to admit making and researching for this video.